Every year, tens of millions of tons of this metal enter our daily lives. But almost no one sees the long industrial journey that turns raw stone deep underground into a foundation of modern civilization. Every year, the global mining and metallurgical industry produces roughly 20 to 25 million metric tons of copper. This volume places copper among the most widely used industrial metals on Earth, alongside iron and aluminum. From power generation and electrical grids to transportation systems, construction, and digital infrastructure, copper plays a foundational role in the functioning of modern society.
In large cities, copper is embedded in the walls and underground, carrying electricity through power cables, transmitting data through communication networks, and enabling heating, cooling, and industrial automation systems to operate reliably. In manufacturing, it is used in electric motors, transformers, electronic components, renewable energy systems, and countless types of machinery. Without a stable supply of copper, many of the technologies that support contemporary life would simply fail to operate at scale. The demand for copper continues to grow as urbanization expands, electrification accelerates, and renewable energy systems become more widespread. Electric vehicles, wind turbines, solar power plants, and energy storage facilities all require large quantities of copper due to its high electrical conductivity and long-term durability. As a result, copper production is not only a matter of supplying raw material for industry, but also a critical component in the global transition toward more energy-efficient and electrified economies. This massive scale of production depends on an interconnected industrial chain that spans continents. Copper ore is extracted in large mining regions across South America, Africa, Asia, and North America, then processed, refined, transported, and transformed through highly specialized facilities before finally reaching factories and construction sites around the world. What appears to be a simple metal wire or component is, in reality, the end product of a global industrial system involving geology, heavy engineering, chemical processing, logistics networks, and strict quality control standards. But have you ever wondered how copper is actually taken from solid rock and transformed into a material pure enough to carry electricity through entire cities? In today's documentary, we will follow the complete industrial journey of copper, starting from geological exploration and large-scale mining through crushing, concentration, smelting, and refining, all the way to the moment it becomes a usable industrial material. Stay with us until the end to see how raw ore from deep underground is turned into one of the most essential materials of modern technology. I'm Adam, and you're watching Tech Documentary HD. Feel free to support the channel by leaving a like, subscribing, and turning on notifications so you don't miss future episodes. From a technical perspective, copper is a metallic element with atomic number 29. Valued primarily for its exceptional ability to conduct electricity and heat. At the microscopic level, the arrangement of its atoms allows electrons to move with relatively low resistance, which explains why copper remains the preferred material for electrical transmission, motors, and electronic systems. In addition to conductivity, copper offers a rare combination of mechanical strength, ductility, and resistance to corrosion, enabling it to be shaped into wires, sheets, pipes, and complex components without losing structural integrity. In nature, copper does not usually appear in its pure metallic form. Instead, it is most commonly found bonded with sulfur, oxygen, or other elements inside mineral compounds known as copper ores. The most important industrial copper minerals include chalcopyrite, bornite, chalcocite, and malachite. These minerals are distributed across different geological formations, typically within igneous, metamorphic, and sedimentary rock structures that formed over millions of years through tectonic activity, volcanic processes, and hydrothermal fluid circulation. The formation of economically viable copper deposits is the result of long-term geological processes. Hot, metal-rich fluids circulating deep underground
slowly transport dissolved copper through fractures in the Earth's crust. As temperature and pressure conditions change, copper-bearing minerals crystallize and accumulate in concentrated zones. Over geological timescales, erosion and tectonic uplift may bring these deposits closer to the surface, making large-scale mining technically and economically feasible. Before any extraction begins, extensive geological surveys are required to confirm the size, depth, and metal concentration of a deposit. Geologists analyze rock samples, geochemical data, and geophysical measurements to estimate whether the copper content is high enough to justify industrial development. This early phase determines not only where mining will take place, but also which extraction methods and processing technologies will be applied in later stages of the production chain. Once a copper deposit has been confirmed and mining operations are established, the industrial extraction process begins with the controlled removal of rock from the ore body. At this stage, large-scale drilling equipment creates precisely spaced boreholes within the rock mass. These holes are designed according to detailed engineering plans that define their depth, spacing, and orientation. This step is carried out to prepare the rock for fragmentation in a controlled manner, allowing the material to be broken efficiently while minimizing unnecessary vibration and structural damage to the surrounding geological formations. Modern monitoring systems and safety protocols ensure that drilling operations remain within strict mechanical and environmental limits. After drilling is completed, industrial explosives are placed into the boreholes and carefully sealed. The detonation sequence is calculated to direct energy into the rock, fracturing it into manageable fragments rather than uncontrolled debris. This controlled blasting process is necessary because intact rock formations are too dense and massive to be handled by excavation equipment in their natural state. Sensors and timing systems regulate the detonation process, reducing shock waves and limiting the dispersion of fine particles, which improves both operational safety and downstream material handling. Following fragmentation, the broken rock is loaded by heavy excavation machinery into ultra-class haul trucks designed to operate under extreme loads. These vehicles transport hundreds of tons of material per cycle along engineered haul roads from the extraction site to processing facilities. This transport stage is essential to maintain a continuous flow of material through the production system. Fleet management software, vehicle telemetry, and coordinated logistics teams ensure that ore delivery remains consistent, preventing bottlenecks that could disrupt the entire industrial chain. At the processing plant, the ore undergoes size reduction through primary and secondary crushing. Large mechanical crushers reduce rock fragments into smaller pieces to increase the surface area available for further processing. This is done because copper-bearing minerals are locked within the surrounding rock matrix and must be physically liberated before chemical separation can occur. Automated control systems regulate crusher settings to maintain optimal particle size distributions and prevent excessive wear on equipment. The crushed material is then transferred to grinding circuits, where rotating mills further reduce particle size through mechanical abrasion. Water is added to form a slurry, allowing particles to flow through the system and enabling precise control over material classification. This grinding stage is critical because the efficiency of downstream separation depends heavily on how effectively copper minerals are released from non-valuable rock components. Process control sensors continuously monitor particle size, slurry density, and energy input to maintain stable operating conditions. Once adequately ground, the material enters concentration circuits where separation techniques isolate copper-rich particles from waste material. Chemical reagents are introduced to modify the surface properties of specific minerals, enabling selective attachment to air bubbles within flotation cells. As air is injected, copper-bearing particles rise and form a concentrated layer that is mechanically collected. This step increases the metal content of the material significantly,
preparing it for thermal or chemical extraction processes that will remove remaining impurities and produce industrial-grade copper intermediates. Despite the high level of automation across modern copper production facilities, not every decision in this process is made by machines. Experienced engineers, geologists, and plant operators continuously interpret data, adjust operating parameters, and respond to subtle changes in ore quality that no automated system can fully anticipate. The ability to recognize how a specific deposit behaves during crushing, grinding, or chemical separation often comes from years of practical experience, rather than algorithms alone. In many operations, knowledge is transferred from senior technicians to younger specialists through daily routines on site, creating a continuity of expertise that evolves over decades. This human layer of judgment ensures that production remains stable, even when geological conditions change, equipment performance fluctuates, or unexpected variables emerge within the industrial process. After concentration and extraction, the copper-rich material enters the final stages of industrial processing, where it is transformed into refined metal suitable for commercial and technical applications. Depending on the production route, the intermediate copper product is subjected to thermal treatment or electrochemical purification to remove remaining impurities. These refining stages are designed to achieve precise chemical purity levels required by electrical, mechanical, and electronic industries, where even small variations in composition can affect long-term performance and safety. Once high-purity copper is obtained, the metal is cast or continuously formed into standardized industrial formats such as plates, rods, billets, or wire feedstock. These semi-finished forms allow downstream manufacturers to shape copper into components tailored for specific uses, including electrical conductors, heat exchangers, mechanical parts, and structural elements. Throughout this transformation, temperature, cooling rates, and mechanical deformation parameters are tightly controlled to ensure uniform material properties and predictable behavior during further manufacturing. Quality control is integrated at every point of the final processing chain. Samples are routinely analyzed using chemical assays, mechanical testing, and non-destructive inspection methods to verify purity, structural integrity, and dimensional accuracy. Automated monitoring systems track production variables in real time, while trained technicians validate critical measurements and authorize each batch for distribution. Only material that meets defined industrial standards is released for packaging and shipment. The finished copper products are then prepared for transport through carefully designed logistics systems that protect the material from contamination, oxidation, and mechanical damage. Secure packaging, traceability documentation, and standardized labeling ensure that copper leaving the refinery arrives at manufacturing sites with consistent quality, ready to be integrated into the complex industrial systems that rely on its performance. What ultimately reaches our hands is not just refined metal, but the outcome of time, human knowledge, and a carefully engineered industrial process that quietly sustains modern life. If you found this documentary valuable, you can support the channel by leaving a like and sharing this video with others who are interested in how modern industry really works. Let us know in the comments where you are watching from and which industrial process you would like to explore next. Subscribe to the channel and turn on notifications so you don't miss future episodes. Thank you for watching until the end, and may peace and safety be with you and your home.